All right, so for the last part of this unit, we are going to look at energy and light. So the question is how does light relate to particles that we have been studying? So how does it relate to atoms, electrons, things like that? First is, as we saw with some of the research that Bohr and Schrodinger and in turn Heisenberg ended up doing, a lot of that was actually focused on light. So this was stuff like our flame test lab and some of the other experiments that had been done by some of these scientists. And one thing to remember is that light is energy. So light is not matter, it's energy. So light is described as both being a wave and a particle. So first of all, light is actually carried by a type of particle that is called a photon. Photons are these extremely small, massless particles that convey energy of light. And there was a debate for a long time, is light a particle? Is light a wave? Which is it? And by the 1900s, scientists actually had enough information to say it's a wave. But we also know it's really both. Photons are a type of particle that travel in a wave-type formation. So next, I want to look at, well, what are waves? And there's a few properties. So waves are this type of repeating, oscillating, cycling, whatever term you want to use, form. And so I tend to refer to these in cycles. And you can see on the diagram to the right, there is a single wave that is noted there. So it notes where the cycle starts and where it ends. And this is actually what is referred to as a wavelength. Wavelength is the length of one cycle. So you pick a point on a wave and measure how long is it until the next point, that same point. Usually we'll do this with crests or troughs, which I'll talk about here in a minute. But it can be any point as long as you measure from that point to the next wave. So the second property is actually related to the first. This is frequency. Frequency, so if we look at the diagram at the top, this is one cycle. Frequency is the question of, well, how many cycles are happening in a given time? So if you look at the diagram below that, there's an example of low frequency versus high frequency. For instance, with the low frequency, we can say, all right, well, I see 4 peaks, 4 crests of the wave. So that would have a frequency, let's say, for whatever given time this is, we can say it's got a frequency of 4. If we compare those two diagrams, we actually see that frequency and wavelength are inverse of each other. A higher frequency, so for this diagram up here, we actually have 12 crests. So this is 3 times as frequent as our low frequency is. But to become more frequent, the wavelengths have to shorten. So frequency and wavelength are actually inverses of each other. If frequency goes up, wavelength is going to get much shorter. If wavelength increases, frequency is going to go down. And the last two things is crest and trough. I use these terms a couple of times. Crest is the highest point on a wave. Trough is the lowest point on the wave. And lastly, this is what we refer to as amplitude, the measure from the lowest point to the highest point. So we talk about waves because that brings us into the flame test lab and the research that Bohr actually did. And the question became, well, what is light? Or more generally, what is electromagnetic radiation? Light is a type of energy in the universe, and some examples of other types of energy would be electromagnetic energy or thermal energy, so the energy of heat, or chemical energy, the energy that's found in chemical bonds, on and on and on. We are focusing on what is called radiant energy. Radiant energy is energy from the electromagnetic spectrum. And light, visible light specifically, is a subset of that. As I said, it carries energy. The higher the frequency, the higher the energy of that type of light. So there are various types of electromagnetic radiation, and these are measured in what we call frequencies. The higher the frequency, the higher the energy, which you can see in the diagram to the right, on the very left, frequency in hertz. The higher energy waves have a higher frequency and a shorter wavelength. So as I mentioned on the last slide, as frequency and energy increase, wavelength is going to decrease. So our high energy waves are going to be things like ultraviolet light, X-rays, and gamma rays, which some of those we will look at much later in the class. Our low energy waves, these are going to be things that have lower frequencies and longer wavelengths. These are going to be things like radio waves, microwaves, and infrared radiation, or infrared light, which we're not really going to deal with as much. But what we do need to know is that these are much lower energy, they have lower frequency, and longer wavelengths. And kind of right smack dab in the middle, there's a very, very, very thin section that we refer to as visible light. We call this visible light because it is visible to the human eye. And this ranges from what we know as red to violet. So we can't actually see infrared light and we can't see ultraviolet light, but we can see in between. We can see our visible color spectrum. And on this spectrum, the lowest energy light is red light. So going from top to bottom, so lowest energy to highest energy. Red, orange, yellow, green, blue, indigo, violet. Lowest energy being red, highest energy being violet. Lastly, is no matter what the energy of the wave is, light always travels at the speed of light. This is more of like more of a physics concept, but light has a constant speed. The change in energy adjusts the frequency of the light. Higher energy waves will have that the higher frequency, shorter wavelength, but they still move at the speed of light. So what is the effect of energy on atoms and their electrons? Well, we looked at this diagram that I currently have on screen. We've looked at it before. This is one of the initial Bohr models. Remember that atoms will start in a ground state, their lowest energy configuration. All the electrons are in the lowest open orbitals that they can be. When the atom absorbs energy, the electron will become excited and jump to a higher energy orbital. Now this could be going from like 3s to 3p, or it could be going from 3s to 4s. It's just jumping to a higher energy orbital. It doesn't last long. The atom will eventually relax and it will release the energy that it took in, bringing the electron back down. So if we have an electron here, it will relax, fall back down to here, and release what is called a light emission, which is energy in the form of light. So to continue and wrap up this, the atom needs to absorb there has to be a specific amount of energy. And this is what I referred to in an earlier video called a quantum. Once that specific amount of energy is absorbed, so once our electron absorbs enough energy, it will jump to the next level. When the electron relaxes, this energy is released, as I said, as a light emission. It is given off as light. So that's what we saw in the flame test lab. Those those substances were in a constant state of exciting and then relaxing, exciting and then relaxing, exciting and then relaxing, which would cause this, what we saw as a constant color change. The higher the energy released, the higher frequency of light. So some of those things that we saw, like the purples or the greens, were higher energies than the oranges or the reds. There was a higher energy of the light that was being released. And each element will have its own specific signature. This is actually something that is used, and it's tend to be used quite frequently in astronomy. When we put light through a slit and then refract it through a prism, it will give us this kind of very specific pattern, which you can see on the bottom right. This is what is called an atomic emission spectrum. Every element has its own spectrum. Every element is unique. So even though we saw things like, I believe it was strontium and calcium, both were bright red. Even though that was the case, that's what we saw. If we were to actually analyze it in a spectrum, we would see, okay, well, maybe there was more red in one of them than in the other. There might have been more other colors that weren't coming through. And these spectra they're kind of like a fingerprint for the elements. So that's all I've got for you guys for this. And we'll be having our test soon. All right. See you later.